Hi everyone, as Ramiro said, my name is Amber Sneddon and I am a master's student from the University of Cape Town, and I'm going to be presenting sort of part one of my master's research, which is looking at an atmospheric river climatology in the South Atlantic Basin based on a modern image processing based methodology. So to start off with, just a bit of background, what exactly are atmospheric rivers? Now, atmospheric rivers can be described as long, narrow corridors of strong vertically integrated water vapor transport, and they are found in the extratropical regions, transporting water from the tropics towards the poles. And they are a very important source of moisture for many regions globally, contributing a significant amount to specifically winter rainfall totals, but also summer rainfall in some regions. And over here, we've got a bit of a schematic of a series of satellite imagery showing atmospheric water vapor content. And I just want to draw your attention to the bottom right, which is the South Atlantic. And you can see a nice long, narrow plume extending from South America towards Southern Africa. And that is actually an atmospheric river event, one that we've studied in a bit more detail. But yeah, I just want to give you a bit of an idea of what they look like from a satellite perspective. But why is it important that we study atmospheric rivers? As I said, they're very important for rainfall in many regions, but they've also been linked with rainfall extremes and severe floods across the world, specifically in the US West Coast, Western Europe, and the UK, but also more recently in Southern Africa. And while there is a big knowledge gap that exists between Northern Hemisphere and Southern Hemisphere atmospheric rivers, there have been a few studies done for our domain, and it was found that around 70% of the top winter rainfall extremes in our region can be linked with atmospheric rivers in one way or another. And just importantly, atmospheric rivers are associated with the warm conveyor belt of cold fronts. So if there is a cold front that has an atmospheric river associated with it, it can result in a lot more extreme rainfall and yeah, just enhanced orographic rainfall. So yeah, and very important that we study these features and just better understand them so we can better understand how they're linked to rainfall, specifically in our region. So traditionally, atmospheric rivers are detected using a thresholding-based method, and this is either based on the 85th percentile threshold, which you can see in the top left. That is a study done by Guan and Wallace in 2015 that used the 85th percentile to identify atmospheric rivers. But they've also been many thresholding, like predefined thresholds that have been used to identify atmospheric rivers. Typically, the 250 kilograms per meter per second threshold, but there's a lot of disagreement as to what this exact value should be, and also the atmospheric water vapor differs from region to region. So there's a lot of disagreement as to what values should be used to identify atmospheric rivers, and also many algorithms are very sensitive to, well, thresholding based algorithms are very sensitive to the values that are fed into them. So yeah, there's a lot of disagreement between what values should be used, and this lack of agreement between models has led to an inter-comparison project being developed that sort of tested all the different algorithms against each other. And on the right, you can see the outcome of this inter-comparison project, where outlined in red, we've got an atmospheric river that they used based on their algorithm. But then that dark blue blob in the middle is the only place where 10 different detection algorithms agree that there was an atmospheric river. So this, coupled with the need for something that's a bit more robust and less sensitive to the values that are fed into it, has led to other methods being explored. One of these is using image processing to identify and track atmospheric rivers. And this is the approach we've decided to take for my research because as being a part of EERIE, we're going to be using different model outputs, and we don't know how the values are going to differ. So we want something that's a bit more robust. So what we've done is we've found a detection algorithm called IPART, which uses top hat reconstruction image processing. I'm not going to get too much into what that is, but just basically, this figure that you can see here sort of explains what top hat reconstruction is. So on the top left, we've got the integrated vapor transport, or IVT field, and you can see that nice dark blob in the middle. That is an atmospheric river. And then top right, you can see the atmospheric river has been outlined in black with its axis in the white dots. But what IPART does is it identifies bright objects on a dark background. So in this case, our bright object is going to be the atmospheric river, and the dark background will be the background IVT field. So on the bottom left, you can see what it's done is it's taken the bright object, which is the atmospheric river, and subtracted it from your background IVT field. So you can see where the atmospheric river should have been. It's outlined in black. You can see that's actually been subtracted. And then next to that, we can see the anomaly or the atmospheric river just pasted onto the domain. So essentially, iPod uses this method to sort of detect features without using too much of the actual like values associated with each feature. So this is nice because it's a lot less sensitive than traditional methods. So we decided it was a really good method to use going forward. So what we've done is we've been using ERA 5 reanalysis data to test this algorithm to see if it works for our region. And yeah, so what we've been doing as a big part of this is performing a lot of sensitivity tests because when we ran iPod just as it comes, we found a lot of issues with it just for our region because it was built for the Northern Hemisphere. And here, this figure you're looking at is just a sequence of one particular atmospheric river event, but iPod didn't even consider it to be an atmospheric river. So to us who study atmospheric rivers, this is very clearly an atmospheric river feature. It's nice and dark, high concentrations of integrated vapor transport, but iPod wasn't even picking it up as an atmospheric river. So we found, this was a big problem. So we found it important to run a series of sensitivity tests, and we ran 12 different sensitivity tests, just testing sensitivities to things like integrated vapor transport thresholds, length-width ratios, minimum areas, and a few other things, just to try and see if we could get the algorithm to work a little bit better for our region. So I'm just going to walk you through visually what this looked like, very basically. So yeah, here we're looking at two different time steps. So two different, well, it's the same atmospheric river, but a few time steps later. But on the top, you can see, I don't know what's going on there, a lot of different shapes. It's not really performing very well at picking up the atmospheric river, which is that green blob. And then underneath, we can see the algorithm doesn't even pick up an atmospheric river at all, which is a bit of a problem. So the first thing we did was we were going to try and see if we could get the algorithm to pick up that feature on the bottom and also separate that strange feature we're picking up on the top. So iPod comes with a customizable parameter dictionary, and the first thing we decided to change was a setting where you can separate maximum peaks, so separate atmospheric rivers into individual systems as opposed to grouping them all together. And doing this already made a really big difference, where we see we've separated that strange blob on the top, we've actually eliminated one of those smaller blobs, and then on the bottom, we've now actually identified that system as a system, which is amazing, but still not really performing too well. We want, as I said earlier, atmospheric rivers are typically long, narrow plumes, and these are not very narrow. So through a series of many tests and changing a lot of different settings, we eventually end up with this. I'm not going to walk you through every single step, but yeah, this is our chosen set of parameters that we've ended up going with. And you can see we've now outlined that that region of high IVT as atmospheric river, and yeah, performing a lot better for our region. So this is the actual results of the sensitivity tests we've done. I'm not going to go into too much detail, but just basically on the left, we've got total count, and on the right, we've got duration. And then within each plot, going from left to right, we're going from less strict to more strict tests. And on the far left, we've got the original settings. So we found that setting the single dome true, so separating maximum peaks, had the biggest difference with atmospheric river counts, because now we're going to have more systems as opposed to big blobs combining systems together. And then as the settings get a bit stricter, we're getting less and less and less atmospheric rivers, because now we're being a bit more selective and not just counting any random shape as an atmospheric river. And then in terms of duration, we found that the sort of mid-range tests tended to have the longest lasting systems, and the original parameters tended to have shorter lasting systems overall, because they were picking up a lot of non-ARs as ARs. And then the same thing here with length and width. So length on the left, width on the right. We found that the single dome true setting tended to make a big difference in the atmospheric river length, because now we're picking up smaller systems as opposed to really big blobs. And then we also found that as we got stricter with our testing, the width of atmospheric rivers tended to decrease. And we saw that when I walked you through how the actual sensitivity test worked, where we get nice streamlined systems as opposed to big blobs. And then we also looked at how IVT and area were affected, and unsurprisingly, setting a minimum IVT threshold tends to increase the mean IVT of systems, which you can see on the left. And then as we applied stricter tests, the overall area of systems tended to decrease because now we're going from big blobs to nice small streamlined systems. So yeah, after all of those sensitivity tests and a very in-depth analysis of snapshots of atmospheric rivers, we determined the best set of parameters to use going forward to build our climatology was going to be an integrated vapor transport threshold of 100 kilograms per meters per second, a minimum area of 100 kilometers squared, and a length width ratio of 3:1. And this essentially helped us to avoid detecting atmospheric rivers features that were definitely not atmospheric rivers and missing very clear atmospheric rivers. And yeah, so from this, we were able to build a nice climatology from 1979 through to 2023. And I just want to show you this figure because this shows nicely how IPOT tracks a system through time. So it's actually able to link up systems using a linkage scheme. So we can get all those snapshots essentially put together into one system, and then you get unique IDs for each system. And yeah, so now we could actually go into some analysis. And the first thing I wanted to look at was where atmospheric rivers tend to originate in our region. And the first thing we can see here, so this is just the genesis points, or like the first time, the axis of the first time step of each atmospheric river overlaid over each other for the whole climatological period. And immediately we can see that atmospheric rivers tend to originate much more frequently in the western part of our domain, specifically over the South American continent and the western South Atlantic, and then much fewer originate in the east towards southern Africa. And we've got a nice concentrated band of atmospheric river genesis towards the east of the Andes, with that white blob on the left. You can see that that is the Andes mountain range, so we're not getting any formation over there, but then a nice long region of concentrated atmospheric river just to the east of that. But this doesn't really tell us too much. So the next thing we did was break this down into seasons. So here we've got just a seasonal analysis of atmospheric river genesis points. Not going to go into too much detail about austral spring and autumn, but I do want to talk about the big differences we saw between summer and winter. So top left, we've got austral summer, DJF, and then bottom left, we've got austral winter, JJA. And immediately there's a big difference we can see in the genesis points of atmospheric rivers, where in austral summer, we see sort of two hotspots of atmospheric river genesis. One quite far south, and then one a bit more towards the equator. And we think that this pattern we're seeing is as a result of the different configurations of the South American low-level jet, as well as the South Atlantic convergence zone, which is very prominent in summer. And then in austral winter, we've got a very concentrated region of atmospheric river genesis towards the east of the Andes, but it's very indicative of the no Chaco phase of the South American low-level jet, which is a lot more common in winter. But we can see also something nice to note is that atmospheric rivers do tend to form sort of throughout the South Atlantic towards Southern Africa as well. But for us, what we really wanted to know is where the atmospheric rivers that affect us in Southern Africa, where those tend to form, so we can get a bit of a better understanding of just those characteristics, and then we can maybe better forecast them and better predict when they're going to make landfall. So what we did was we took inspiration from work done by Blamey et al. In 2018, and we drew a north-south line to the west of Southern Africa and used this as a proxy for landfalling atmospheric rivers. So each time an atmospheric river axis crosses that line, we would count it as a landfalling atmospheric river, and we were able to build a database of just landfalling atmospheric rivers. And then we were able to do the same thing and look at the genesis points of these landfalling atmospheric rivers. And what's nice is we can see that there's actually a lot less genesis over the South American continent, but a lot of genesis throughout the South Atlantic for all seasons. But again, I just want to draw your attention to the bottom left, which is austral winter. And we can see we've actually got a lot of atmospheric rivers forming over the South American continent, the same sort of hotspot that we saw for all atmospheric rivers, just towards the east of the Andes, again showing a very a pattern that's indicative of the no Chaco phase of the South American low-level jet, and then traveling all the way across. We've got genesis traveling all the way across the South Atlantic towards us, and just very important. Well, we're focusing on winter because typically most of our rainfall that we get that's associated with atmospheric rivers is during the winter. But yeah, I want to go into a bit of, this is a very rough figure, but what we're seeing here is a couple of hotspots of atmospheric river genesis that is very much in line with work that was done by Ramos et al. So this is a figure that I've kind of taken inspiration from Ramos's work, and they found 4 hotspots of moisture uptake for atmospheric rivers in the South Atlantic. Actually 2 hotspots just off the coast of Southern Africa, so right near to us, and then one sort of, I don't know if you can see my mouse, but just off the east coast of South America, and then one quite far inland in the Amazon River Basin. And we see this pattern sort of indicated in all of these, in all seasons. We can see those sort of hotspots coming out, not very clearly, but there's signs of them, which I think is really cool. And then I also just want to explain the South American low-level jet configurations briefly. So on the left, we've got the Chaco jet event configuration, and on the right, we've got the no Chaco jet configuration. And just importantly, we can see that the no Chaco jet event transports moisture eastwards before it reaches 25 degrees south, and we sort of associate this phase with a lot of that landfalling atmospheric rivers, and we can see that signal specifically in winter over here, where a lot of the atmospheric river genesis tends to occur just around 25 degrees south over the South American continent. I just think that's a nice thing to note, and allows us to link our work to Ramos et al.'s work from 2017, 2018. The next thing we did was look at just the overall general climatology for atmospheric rivers in the South Atlantic. So what we found when we looked at it annually is that there are around 160 atmospheric rivers per year in the whole domain, of which about 26 make landfall on Southern Africa. There's also a lot of variation, interannual variation between the number of atmospheric rivers that exist within the whole domain and those that make landfall. We are yet to actually analyze this and work out the patterns with this, but that is on my to-do list. But then, as I've said earlier, for us, a lot of our atmospheric river associated rainfall occurs during winter. So then we went into a bit of a deep analysis into the winter climatology, and again found quite a lot of interannual variability, with about 77 atmospheric rivers occurring in the domain on average per year, of which about 16 of those make landfall. What was really interesting to us is we found that the number of atmospheric rivers is not necessarily correlated to rainfall, because if you look at 2017 and 2018 over here, you can see we have above average number of atmospheric rivers making landfall on Southern Africa. But I don't know if you guys probably know about it, but from 2015 to 2018, we had a really bad drought in the Southwestern Cape, known as the Day Zero drought, where we were having far below average rainfall occurring. But here we can see we've got above average atmospheric rivers, which tells us that there are other factors that come into play in terms of whether atmospheric rivers bring rainfall or how intense the rainfall is. And there've been a couple papers recently that have been released showing that the angle at which atmospheric rivers make landfall has a big impact on the amount of rainfall, the type of rainfall that is associated with them. So we're going to hopefully be able to go into a bit of analysis on the angle of atmospheric rivers in the future, but yeah, haven't got there yet. And yeah, just in terms of what we're planning on doing next, so I've been in the process of writing up my first paper, and what we're currently doing is comparing what I've got with this atmospheric river database to a global atmospheric river database, just to sort of see if our results are comparable. And then the next step is to compare our results to the EERIE models. So far, we have the nextGEMs dataset and have done some preliminary testing, but we need to do a direct comparison to our results using ERA5, and then we also want to look at how resolution of the different models affects our atmospheric river database and what we're seeing in terms of rainfall intensity and atmospheric rivers in general. And yeah, that's me for now. Thank you.
Thank you, Amber. Very interesting. Thanks for the clear presentation. Is there any question? Thomas?
Yeah, thank you very much, Amber. Very interesting. I mean, one of the question, and probably it's currently not sort of high on the priority list of your research, but I mean, you may wonder how things change in a warming world, right? And you didn't see really much, right? In some of the time series you have shown, I mean, it looked all fairly stable. Having said that, I was wondering a little bit, you know, the way you define things, you know, you use certain thresholds, like, you know, a certain moisture flux. And, you know, if this changes in a warming world, I mean, is it really, I mean, I can imagine it's actually quite tricky to make statements about changes of these atmospheric rivers, given the way they are detected at the moment. Could you comment on that? Or?
So we've identified that as a problem. For us, the main thing was we wanted something that was a bit more robust for comparing the different model outputs, because we don't know if the values are going to differ. But it also will help us have something that's a bit more robust in a warming world, where we might have different, or we probably will have higher water vapor values going forward. And this kind of takes away some of the uncertainty associated with traditional methods, because it is a little bit more robust. And I know I said that we're not using thresholding, but then proceeded to set thresholds within IPART, but that's just sort of to refine the sort of size of systems we're picking up. So it is a bit more robust. I'm not saying it's perfect. I don't think there is a perfect method as of yet, but I think it is a slightly better, more reliable method to use for future projections.
Okay, thank you.
Any other question? I have one, Amber. I was just wondering, well, I come from South America, so it's very nice to see that when we leave our systems towards the Atlantic, you pick them up over the other coast over Southern Africa. I was just wondering about the higher frequency of ARs you detect in winter, if it's, I mean, explained because of the, let's say, larger barganicity, or because of the, in principle, I was just looking at the maps you were showing as a function of the season. And if there was, or if you saw, if there was any relationship regarding, let's say, for example, the strength of the westerly winds, which could connect in some way what is emerging from South America and reaching eventually South Africa, or if you can give some insight on this, let's say, season-dependent frequency of ARs.
That's a good question. So we actually found in general there were more systems in summer because there's more moisture availability and more convection. But those systems tended to be more concentrated over the South American continent and in the western portion of our domain. But in winter, with there being less systems, more systems tended to actually make their way across towards us. And obviously, with the shifting of the heat equator, they're more likely to actually make landfall on Southern Africa. But yeah, I think the strengthening of the West Sea wind belts, combined with the shifting of the heat equator, meant that we were getting more intense systems that were longer lasting and more likely to reach us. But overall, we did see more systems in the whole domain during the summer months than in the winter.
Okay, great. And also you mentioned in the beginning, sorry. Please go ahead.
Sorry. Also in winter, we do tend to get more mid-latitude cyclones, and atmospheric rivers are associated with, well, they've been shown to be associated with cold fronts and mid-latitude cyclones. So the more this, you can see they actually tend to follow the storm tracks in winter. So yeah, I think that'll play a big role in the atmospheric rivers actually making their way across the South Atlantic towards us.
Great. Yeah. Sorry for interrupting. I was just about to ask about this higher frequency of fronts, about whether this would enhance or let's say give more likelihood of these ARs reaching your coasts during the winter season. So well, thanks for clarifying it. Is there any other comment or question or for Amber? Okay, so thank you again, Amber, for your presentation.
Thank you.
Now we can move on to our second speaker, which is Martín Lotto. He will speak about leptospirosis outbreaks over Southern South America, some of the region from where the moisture that Amber analyzed is coming from, Argentina. So, Martin, the floor is yours.
Thank you so much. I can see a mirroring image of my screen. So I'm not entirely sure if I'm sharing screen already. But I guess so. Yeah, you can see my screen, right? Yeah. Okay. So this is going to be a fairly different presentation to what Amber just talked about, and I'm very glad that I have this opportunity, because usually we tend to speak to people who are from our same field, and yeah, it's nice to just cross borders with that. So today I'm going to be talking about leveraging Earth observation data to predict leptospirosis outbreaks in Argentina, which is a work that we've done throughout the past, I would say, 5 to 6 years. And that is feeding directly into what we're going to be doing with EERIE in the second half of the year. So just to give a little bit of a background, because I don't come from climate or physics, I'm actually a biologist. And I've done my master's and PhD in epidemiology, so I couldn't be more farther away from these fields. And I've done also some field epi work in Ecuador, so I've been moving around Europe and South America. And then in 2022, I landed a position here at the Barcelona Supercomputing Center within the Global Health Resilience Group with Professor Rachel Lowe. And one of the things that, I would say pretty much all of the things that we do are trying to understand how climate affects dynamics of specific diseases, which we call climate-sensitive infectious diseases. And then we try to develop some sort of a tool or an indicator or whatever might help decision makers from different public health agencies to make decisions and develop strategies, right? So when it comes to climate-sensitive infectious diseases, basically there is a whole bunch of diseases that are sensitive to climate, but we focus on a specific group, which are either vector or arthropod-borne diseases. And that means that the main transmitters or the main links between the pathogen and the human, in this case, are either rodents or ticks or mosquitoes or flies, etc. And by their nature, they tend to be quite vulnerable if we want to changes in land use or precipitation, and they are typically related to extreme weather events like flooding events or heat waves. But I always try to make the same footnote, which is we tend to associate these diseases with extreme events. And we don't have to forget that these diseases also obey to seasonal patterns. So we are typically going to see, for example, in Germany or now more than ever in Northern Europe, we're going to see that tick-borne diseases are peaking in spring and summer. And that's because ticks just reactivate after winter and people start going on hikes, and that's when they encounter each other. And this is particularly important because, of course, like I don't have to convince any of you that we are facing a global warming. And this is just an indicator that I like using, which is just the increase in daily global surface air temperature. But I always say this is not the only thing that is going on. We see many shifts in other climate indicators like precipitation, etc. So given all of these, CSATs, like we call them, are very important nowadays. And I'm going to focus on one of these, which is the one that I worked on part of my PhD, which is leptospirosis, is caused by a bacteria, a spirochete of the genus Leptospira. And it causes, depending on where you are on the globe, it causes roughly 1 million cases each year, with on average 60,000 deaths. And most of the cases go unnoticed because they don't have symptoms. And some of these progress to severe disease if they go untreated. So by default, if we know that we are in a leptospirosis season or that we have the good conditions for disease, even if depending on the country anyways, but it is regularly treated, even if you don't have any symptoms, because we don't know how severe it can get. And one of the interesting things about this system is that it involves many different links. So it's not very simple that you're going to get an infected rodent and then they're going to bite humans, for example, like what you get in dengue. You actually need to disturb rodents in a way so they get closer to humans. So that's it. That is typically what we see when we have a flooding event. So rodents might lose their nests and they're going to seek refuge in the human population. And typically what they choose is those who are closer to water banks. And usually they are vulnerable populations. So they pee, and that's when people who have cuts on their skin, they get in touch with the bacteria, and that's how infections occur. But that's not the only way. The bacteria keeps its cycle between different animals, and for example, fishers, or people who work nearby water fields, they tend to get exposed more often. But like I said, we are, in this case, we're mostly interested in the effect of extreme weather events, and that's when the El Niño Southern Oscillation comes to play. In particular, the El Niño events are, I mean, I don't have to explain that to you probably, but you know that in Latin America and the Caribbean, we don't only get one response during El Niño events. We get a mixture between dry events and humid events. And we can see that in these areas where we have a larger amount of precipitation and that can lead to increases in river height, we tend to see outbreaks taking place. For example, here in Argentina, where my work was based. So this is what I was talking about. So you see that here we have Argentina, and northeastern Argentina is this area over here. And I focused in these two provinces, Santa Fe and Entre Rios, which are neighboring provinces, and they have a very big river in the middle, the Paraná River, which is very prone to flooding events. And this figure is from the work done by Soledad Lopez and colleagues, which are actually colleagues that we have in common with Ramiro. And we've built on their work. So this is what typically what a typical epidemic curve for leptospirosis looks like. This covers between 2009 and 2021. And this is the curve that epidemiological curve we worked with when we published the first paper. And you see that there are fairly irregular outbreaks, or what they seem to be irregular outbreaks or irregular peaks. And they are actually very synchronized with Niño events. So for example, we have here in 2010 a big spike that is associated with positive anomalies in the Niño 3.4 region. But then you can also see that in 2016, it's not that big, and we had a very strong Niño year, and that's probably because we had flooding events in these cases, and people were evacuated, and there was an immediate response for controlling the consequences of the floods. So nowadays, this is very important because we are facing in Argentina, in this region, we're facing major floods going on right now after the big storms are taking place. So this is something that still is of relevance and will continue to become of more relevance in the near future. So basically what we do is we take as much information as we can from climate, in this case, river height from Paraná River, monthly precipitation, monthly temperature, etc. And we try to find and quantify the association of each one of these variables with the risk of acquiring leptospirosis. And we do that by using hierarchical mixed models, using a Bayesian modeling framework. I didn't want to get too much in the details of the modeling framework, but I'm happy to discuss about it. And basically, we put that together with surveillance data at the same spatial and temporal resolution. We fit the models, and then we validate the models by doing cross-validation, different strategies of cross-validation depending on the structure of the data. And we get either relative risk maps and over probability figures and results. And this is a nice opportunity for sharing with you that all of these tools that we're using for fitting these models within the context of another project that we're working on, which is nextGEMs, we're developing our tools, our packages that allow users to recreate exactly our workflow. So if any of you is interested in knowing a little bit more about that, I'm also happy to share with you. So by the end, in this leptospirosis study, what we found is that using the El Nino 3.4 index 3 months in advance of an outbreak month gave us a fast approach to the probability of an outbreak. And then we updated the probability of an outbreak 1 month before the target month using monthly total precipitation and the river height of Paraná River. And the height of the Paraná River, sorry. And so this was a really nice outcome because it allowed us to have a two-stage forecasting approach for disease outbreak. And when we compared that with current practice in Santa Fe and Entre Rios, we found that the first step of the Niño model would increase the prediction ability by 9% in Santa Fe and 39% in Entre Rios. In Entre Rios, it was quite responsive. And then 1 month prior, using local climate data, increased by 17 and 29%. So these work got together with the work that we've been doing in the group with dengue, malaria, and this doing in this case in a common project for Latin America and the Caribbean called ENCAST, for El Nino Disease Forecast. And we partnered with all these different institutions and universities. And the idea behind this was to develop a platform where, or in this case, is a Shiny app that public health agents or different partners could have access to and get real-time short and medium-term forecasts of disease outbreak. And for leptospirosis and for leptospirosis in particular, we focused on northeastern Argentina and southern Brazil. And the users could encounter load, for example, these bulletins that let them know how it looks in the near future. So based on the experience that we've had with ENCAST and also how responsive leptospirosis is to changes in climate and particularly to El Nino, we started this partnership with our colleagues from the climate variability group, and we joined EERIE. And basically what we want to do now is to use the model outcomes to enhance our understanding of the system. So for example, what we are actually interested in doing right now is in the second half of the year, once we have more outputs from the simulations, we would like to see what happens all the way towards, if I'm not wrong, actually it's not towards 2100, it's actually until 2050. And we want to compare what happens in different scenarios, combinations of scenarios of SSPs and RCPs, and report the leptospirosis risk anomalies in these two different provinces. Of course, these are simulated data. We're not entirely sure what's going to happen once we do the calculations. And then the other step that we want to do is, as the outcomes become more available, to compare what happens when we increase the resolution of the simulations. So are models becoming performing better, or they're actually performing the same as what we have in different quarter resolutions. So actually, I realize that I'm speaking probably a little bit too fast because I'm almost done. The idea behind this is to kind of create a feedback between two different work packages. So we are, on the one hand, in WP8, we are in the second half of the year, we're going to be doing quite a bunch of modeling with the results from the simulations. But also at the same time, we're working with the storyline creation with WP2, which is a really interesting way of, in a way, transforming what we get in very complex numbers from the modeling phase into something that public health agents and the people can understand and relate to. So we strongly believe that that's the way that we can achieve people to listen to us. So with that, I want to thank you all, and I'm happy to answer any questions or comment any further on whatever topic.
Thank you, Martin. Thank you. It was a very clear presentation. Is there any question, Thomas?
Yeah, thank you very much also from my side. I mean, that looks very promising, and I understand it's early days because you're still waiting for the model results. I mean, certainly when it comes to looking into the future. And it's also great that you're sort of engaged in the storyline part. What I was wondering, do you have contact to stakeholders in that region? So could you elaborate a little bit on that?
Well, it changes between countries, to be honest. So, for example, in Argentina, right now we're still at the university level, so we're not really engaging directly with policymakers, which is actually our target. But in southern Brazil, we have more clear access through the Fiocruz Institute. I don't know if you're familiar with that institution, to public health agencies. With NCAST, for example, we work hand in hand with the Barbados Public Health Agency. So that's the strongest relationship we have with policymakers. But right now, NCAST is only focused on dengue in Barbados. So it changes. In Colombia also, we have a strong university-focused link. Yeah, so right now, I would say it's a fairly early stage in terms of stakeholders.
Okay. And just a follow-on question, I mean, sort of how transferable are your models? I mean, from what I understood is sort of you build your models, they probably have some regional flavor, right? Or are they, I mean, but, these questions may be also of interest or are of interest in a sort of warming world for Europe. Sort of how transferable would the methods be?
They are 100% transferable. So in our group, we have work done in West Nile. You can see what we've done using the same modeling framework by Giovenale Moirano. He published recently his work on West Nile virus. So basically, you can think of them as just as statistical regression models. And what we do, the workflow is fairly linear in terms of it doesn't matter if you change the region. So first we assess the correlation, we assess the formulation of the priors because we're using a Bayesian modeling framework. And then we select what best candidate lags are, because we don't assume that the effect is immediate. We assume that there might be a delayed effect of 1 month, 2 months, whatever. And we test a whole range of them. So in the end, we end up testing a lot of models for each one of the regions, but the workflow is the same, remains the same.
Okay, thank you.
No problem. Thank you for the question.
Any other question? Well, I have one, Martin. I was just wondering about this perturbation you mentioned on the rodents, where they just basically leave their nests and eventually have an encounter with a human being. I was just wondering, you mentioned floods, which I think might be let's say, the hardest affectation to rodents, but thinking of weather, climate inputs, I mean, are they affected by, for example, extreme heat events, or when the Paraná River is very low, the lack of water or food or whatever, is it also a perturbation? Or
it is, but we are not entirely sure how that affects or how that translates into disease dynamics. And the limitation we have here. So let me answer the first part. Let me answer the question directly, because you're asking me from an ecology point of view. And yeah, there is a perturbation because it's going to affect the population size of the rodents and probably the survival of their entire colonies, if we can call them colonies. But we're also interested in seeing how we can link rodent dynamic with disease dynamic. Okay, so that's what our models are in the end doing. And the problem we have here is that leptospirosis is overall, when you don't have an event, is very low. So it stays always near zero. And only when you have extreme precipitation or flooding events, you see the spike. But then you don't see that translated into disease when you have a drought, for example. So even though that's very useful for us because that makes leptospirosis very responsive to extreme precipitation, etc., it doesn't mean that we can, by understanding rodent ecology, it doesn't mean that we can translate that into disease dynamics necessarily. Does that make sense?
Yeah, it does. It does. And just out of curiosity, I know nothing about this. Is leptospirosis also present in Europe, or is it just?
Yes, but so here we actually have more hantavirus in Europe, and it's actually a big concern in Germany. So I don't know. Yeah, who am I talking to? So you know that a couple of years ago in the area of Cologne there were big floods, and hantavirus was a main concern in the area. But not only there. So hantavirus it's transmitted in the same. It's caused by a virus, but it's transmitted in the same way as leptospirosis. They kind of compete with each other. And what we see here in Europe is more frequently hantavirus than leptospirosis. But there is definitely leptospirosis, and there is quite a bunch of work being done right now by different research groups. To understand how climate impacts lepto here.
Okay. Thank you, Martín. Well, thanks again to Martín, also to Amber, first for agreeing to join these presentations and for giving insight into how EERIE is feeding or will feed your research. Thanks again. Both have been very clear with your topics and how you presented the results. And thanks to all of you for attending the meeting. Just a short advertisement before finishing. The next session will be on the 16th of June on WP12. Hannah Christensen will be presenting, will be the host. And we have two very interesting talks, one by Simon Michel, who will be talking about machine learning insights into differences between high and low resolution climate models, and also by Diayang Atmosho. She will be talking about data-driven equation discovery of a sea ice albedo parameterization. So this will be on the 16th of June. It will be also Monday at 2 p.m. as usual. So that's the advertisement for the next month. So thank you all for attending, and well, hope to see you soon.